So welcome to the next topic in IGCSE Chemistry, energetics of reactions. Okay, so we're going to look at the energy of reactions. So what we will learn, again, we have learning objectives. We're going to learn about exo and endothermic reactions, describe something called calorimetry and do some experiments around that, calculate heat energy changes, interpret some energy level diagrams, calculate something called molar enthalpy change, okay, from heat change. We'll be defining these terms, so don't worry about that. And for those doing triple point, describe endothermic processes and exothermic processes in terms of bonds. Draw and label energy diagrams for both exothermic and endothermic reactions. Calculate energy of a reaction using bond energies. Draw and explain reaction profile diagrams showing delta H and activation energy. So we'll start off with exothermic reactions. So there's an image there of an exothermic reaction. So exothermic reactions release heat energy to the surroundings. So basically they feel hotter when the reactions are occurring. And what happens is the chemical potential energy of the chemical bonds inside the reactants and going to be greater than the chemical energy of the bonds of the products, okay, because that bond energy has been released in the reaction. That's what you're feeling the heat for, okay. And this is known as an energy time graph, and you can see here that the energy of the reactants, okay, this guy here, is going to be greater than the energy of the products, and the energy difference is going to be released, and that's why you can feel it. That's why it's hot to touch in the test tube. And we also have endothermic reactions there. There's an example of an endothermic reaction where in endothermic reactions, basically the reaction takes heat energy from the surroundings and so gets colder. So the chemical potential energy of the chemical bonds in the products is now more than that of the reactant. Okay, so again, we have the diagram here. So the reactants are actually in lower energy. They gain energy from the surroundings. So that means that the energy of the products is going to be greater in terms of the bonding, or the energy of the bonds. Okay, and the difference in heat energy, this here, is going to be taken from the surroundings. So again, looking at exothermic reactions, here's an example. Okay, so the neutralization of an acid by an alkali, which you would have done last year, is an example of an exothermic reaction. Okay, so acid plus alkali gives salt plus water, but it also provides heat energy. Okay, so some heat energy involved. And the symbol to show a change in the amount of heat energy is delta H. Okay, pronounced delta H, and we're going to look at that in more detail later in the lesson. But essentially what happens is that heat energy is released. Okay, so we've looked at exothermic reactions. Now let's look at endothermic reactions. Endothermic reactions are not as common as exothermic reactions, but here's one example. Dissolving ammonium nitrate crystals in water is an endothermic reaction. Okay, so ammonium nitrate, you dissolve it in water, you get ammonium nitrate solution, and you've also got a loss of heat energy. Another way you could say is that heat energy is required on the reactant side. Okay, it requires heat for the reaction, heat from the surroundings for the reaction to occur. Okay. So the temperature of the reactants, ammonium nitrate plus water, is around about 20 degrees, depending on the amount of water you've got. And the temperature of the products, okay, so energy is not a product, so it's only the ammonium nitrate solution, is going to be around about 13 degrees, again, depending how much you've got in the test tube. Okay, so there's a 7-degree difference. And that 7-degree difference is being used by the reaction to allow the reaction to occur. So it actually is taking energy from the surroundings So that's your minus heat energy, rather than giving it. Okay, so let's complete the following table. So from your previous experiences with chemistry over the last few years, are the following reactions exothermic or endothermic? Okay, so pause the video now and see if you can answer whether they are exothermic or endothermic. Okay, so welcome back. So iron and sulfur to make iron sulfide. So initially you're using a Bunsen burner to heat the iron and sulfur, but as soon as the reaction starts, a lot of heat is released. So that makes it exothermic. Okay, photosynthesis, so from biology. So in photosynthesis, the light or the energy from the sun is being used by plants and their chloroplasts to transform carbon dioxide and water into sugar. So you're using energy, so it's going to be an endothermic process. Okay, mixing barium hydroxide and ammonium chloride. I don't know if you've done that before. It's a very cold reaction. Okay, it's endothermic. Energy required from the atmosphere or the surroundings to let that reaction occur. Adding water to calcium oxide. It's a very exothermic reaction. Okay, and mixing silver nitrate and sodium chloride, also a precipitation reaction, which is exothermic. The test tube actually heats up. Okay, so hopefully you got 5 out of 5 for that. Okay, so moving right along. So we've already looked at delta H briefly in the previous slides, but we're going to kind of develop and focus on that. So what's the relationship between endothermic and exothermic reactions and this thing we call delta H? Well, for an exothermic reaction, delta H is negative, okay? It's the amount of energy difference between the reactants and the products. Okay, this means that the heat has been lost in the reaction. Whereas if the products have more energy than the reactants, then it's going to be delta H is positive. That means heat has been gained in the reaction. Okay. So just recapping, for an exothermic reaction, heat is given out and delta H is negative. And for an endothermic reaction, heat is taken in and delta H is positive. Okay, so another word for the heat energy, Q, of a content of a compound, is its enthalpy. Okay, so it's the amount of heat energy that's released when you're breaking all the bonds. Okay, just think about that. It's going to be enthalpy. We're going to be introducing it later. Okay, because you can calculate enthalpy change, Q. So you need to know that the unit of energy is the joule, okay, from physics, and also nice to remember because we're dealing with such numbers, that 1,000 joules is 1 kilojoule. Okay. So how do we do these calculations? Well, let's look at the enthalpy of combustion of a fuel. Okay, the amount of energy released or absorbed in a reaction can be measured using a following formula. Q equals M times C times delta T. Now you're probably thinking, what do those letters mean? Well, basically it's saying Q, the heat energy in joules, equals the mass of water, okay, M stands for mass, and that's in the units of grams, times the specific heat capacity of water, which is about 4.1, which is in the units of joules per kilogram per degree Celsius. Okay, that's C, times the rise in temperature, okay, the change in temperature, because it could also be negative, okay, which is delta C. But for fuels, obviously, it's going to be exothermic, so delta T will be positive. Okay, so here's an example, and this is the experiment that we tend to use. Okay, we use something called a calorimeter. Okay, so in the calorimeter you have basically a beaker, so made of copper this time, because copper is metallic and it's going to conduct the heat which is coming from the spirit burner. Okay, so inside this copper calorimeter is water. So you're basically heating the water in a copper calorimeter, and it's all blocked off apart from, it's all blocked off from the outside surroundings because you've got something called a draft shield and an insulating card, and stuck in the middle is a thermometer. So it's basically measuring the amount of energy being transferred from the flame into heating the water. Okay, so the measurements you're taking over here, okay, going to be the temperature of the water before heating, the mass of the water that you're going to be using, and the mass of the fuel used. And I guess also the mass of the water, the temperature of the water after heating. Okay, so you have a temperature difference, delta, so that way we can calculate delta T and plug it into the equation. Okay, so here's an example. The temperature of 100 grams of water was increased by 32.6 degrees Celsius by heating with 0.46 grams of ethanol. Assuming no heat loss from the apparatus, okay, this is why we have these shields, okay, it's a big assumption to make. What was the enthalpy of combustion of ethanol, C2H5OH? Okay, so pause the video now and see if you can actually work it out for yourself. Remember, we have an equation now, so you can start using that and come back once you think you have the correct answer. Okay, so hopefully you have an answer. Okay, so we have an equation to start off with. Okay, we've given you the equation Q equals M times C times delta T. Okay, so do we have the mass? Do we have the specific heat capacity, which I should have really given you, bad for me, and delta T. Okay, so the heat energy produced in joules equals the mass of the water, which is given in the question, times the rise in temperature, given in the question, times the specific heat capacity of water, which you will be given in your question, in the exams, and it'll also be in your data book. So it's going to be 100, which is the mass of the water from the question, times the temperature rise, 32.6, times 4.2, which is the specific heat capacity of water. So maybe I probably should have put that in the answer to in the question before I fired the answer at you. But if you bung in the numbers, you get 13,692 joules for 0.46 grams of ethanol. Okay, but we really are looking at enthalpy here. So it's only one of the steps. Okay, so what is the heat energy produced per mole of ethanol? Very good question. Because you need to remember that a mole of a substance is the relative molecular mass in grams. Okay, so the heat energy produced from our previous calculation is 13,692 joules, and that comes from 0.46 grams of ethanol, but we want moles. So the molar mass of ethanol from our last unit is going to be 24, the molar mass of carbon, or of the carbon atom, so 12 times 2, plus 5, which is 5 times the molar mass of hydrogen, of the atomic mass of hydrogen, plus the atomic mass of oxygen, plus the atomic mass of hydrogen again. So it's going to be 46 grams per mole. Okay, so the mass of 1 mole is going to be 46 grams. However, we don't have 46 grams, we've only got 0.46 grams. So the energy released by the combustion of 1 mole of ethanol will be 13,692 times 46 divided by 0.46, because we've only got 0.46 grams. So it gives us a massive number of 1369,200 joules. or 1369.2 kilojoules per mole. Okay. So burning of ethanol is exothermic reaction, so heat energy is lost, delta H is negative, which is what we've seen. So far, so good. Okay, and the molar enthalpy of combustion, delta H, of ethanol is therefore minus 1369.2 kilojoules per mole. There we go. We've got the answer using the calorimeter. Quite a large number. Okay, another thing we could do, instead of working out the enthalpy changes associated with combustion of a fuel, we could work out the energy changes associated with the neutralization reaction. So instead of heating water, we would put an acid and an alkali together in a polystyrene cup, which is insulated. Reason why it's insulated, because we don't want heat from the surroundings coming in, or heat from the reaction being lost. So we basically insulate it, and we bang a thermometer in to measure the temperature change of the reaction, delta T. We can still use the same equation. So the enthalpy of neutralization equals the heat produced when an acid and alkali react to produce 1 mole of water. You could also do a heat of precipitation, where you have two soluble solutions precipitating out to form one precipitate, and you can measure the temperature difference. So here's an example. 50 centimeters cubed of 2 molar hydrochloric acid was added to 50 centimeters cubed of 2 molar sodium hydroxide in a polystyrene cup, and the temperature rose by 13.7 degrees Celsius. Now I've got to be careful here because I've not really introduced the concept of a mole, what capital M is. Okay, so capital M, if we're dealing with solid chemistry, is going to be the molar mass, but capital M in this particular case is just shorthand for us lazy chemists of moles per decimeter cubed, which we've already looked at in the last unit. Okay, so if there are no heat losses and the final volume is 100 centimeters cubed, what is the enthalpy of neutralization? Okay, that's a very good question. So again, this is the reaction, hydrochloric acid plus sodium hydroxide giving sodium chloride salt plus water. It's going to be a 1 to 1 to 1 to 1 mole ratio. So the number of moles in 50 centimeters cubed of 2 molar HCl, okay, is going to be 50 divided by 1,000. Okay, reason why it's 1,000 is because we've got to convert that to decimeters cubed times 2, which is going to be 0.1 moles of HCl. So far, so good. So from the equation, 0.1 moles of HCl will produce 0.1 moles of water. Okay, so water's being created. So that's why we can use, hopefully, the 4.2 number for our specific heat capacity of water again. Okay, so again, using the equation, the heat release Q in producing 0.1 molar, okay, NaCl is going to be M times C times delta T, which equals 100 times 4.2 times 13.7, so 5,754 joules of water, okay, of 0.1 moles of water. Again though, this is the heat release from producing 0.1 moles per centimeter cubed of water. So we need to do some conversions. So it's going to be, what we want, 1 mole, so it's going to be 5,754 times 1 divided by 0.1 joules per mole. Okay, because we want to get to moles. Okay, we've got 0.1 moles, we want to get to 1. Okay, this is why we do this conversion. And it's going to be 57 minus 57.54 kilojoules per mole. Okay, again, quite a large number. Okay, so this makes sense again, because it's an exothermic reaction, delta H should be negative, so we're on the right track. Okay, so energy from fuels again. So this is another way of approaching it. So rather than looking at it from a calorimetry perspective, we can actually look at it from a theoretical perspective. So a fuel is a substance that provides energy. We've already looked at it when we looked at trying to work out the enthalpy of combustion. Because when a chemical fuel is burnt, it's combusted with oxygen, it releases energy, mainly in the form of heat. Okay, some fuels release more energy when they are burnt in oxygen. So here's an example here. So gas, natural gas, releases a lot more than, say, ethanol or even coal. So we really should be using natural gas most efficiently. But how do you get these numbers? So why is there an energy temperature change in chemical reactions? Well, it's because chemical reactions involve the making and breaking of bonds, because there's lots of energy involved in those bonds. So let's look at the burning of methane. So this is the equation. Methane plus 2 oxygen give 2 water plus carbon dioxide. So you have methane there, you have 2 oxygen molecules and a carbon dioxide molecule and a couple of water molecules. So in the reaction, to burn methane or combust it, you have to break all of the bonds in the methane and all of the bonds in the oxygen. This requires, of course, energy. And then you have to make the corresponding bonds in the water and the carbon dioxide. Okay, bond breaking is endothermic. Okay, so energy is always required to be put into the reaction to break bonds. It requires energy to break bonds. Okay, and energy is always taken from the surroundings when a bond is broken. So bond breaking is always endothermic. There we go. Whereas bond making is always exothermic because energy is released when a bond is formed. Bond making is always exothermic. So you can work this out theoretically by looking at bond energies. Okay, so when energy is released when a bond is formed so energy is released when a bond is formed into the surroundings or absorbed from the surroundings when it's broken. Okay, so it's because it requires energy to break the bond. This is called bond energy. So as an example, the CH bond of methane has a bond energy of 413 kilojoules per mole. Quite a lot of energy. Okay, so if you're ever given a question like this, you will be given the bond energies. You don't have to remember them. So here's some examples here of some bond energies. So the hydrogen bond energy is 433, whereas something like the carbon-carbon triple bond, this guy here, is 836. Triple bond, a lot more energy to break. Makes sense. So single bonds require less energy than double and triple bonds to break. Okay, so let's calculate some energy changes. So we're discussing the combustion of methane, which you see in your Bunsen burner. As you add more oxygen, obviously, the bluer the flame, more carbon dioxide being produced. Okay, so how can we do this with bond energies? Well, we now know that CH bond is 413, and the oxygen double bond is going to be 497 kilojoules. Okay, the total for breaking the bonds is going to be 4 times 413 because methane has 4 carbon-hydrogen bonds plus 2 times 497. Okay, it's because there are 2 double bonds in oxygen, in the 2 molecules of oxygen. Whereas when we're making bonds in the carbon dioxide, there is the carbon-oxygen bond, 732 kilojoules, and the OH bond is made 464 kilojoules. Okay, the total of making the bonds is going to be 2 times 232 because carbon dioxide has not 1 but 2 carbon-oxygen double bonds, and there's going to be 1, 2, 3, 4 oxygen-hydrogen bonds to be made. Okay, so the total energy required to break the bonds is going to be minus 264 kilojoules per mole. The total to make the bonds is going to be 3,320 kilojoules per mole. So we can do some subtracting. The total energy change, therefore, between the reactants, these guys, the methane and the oxygen, and the products is going to be 246 minus 3,320. Okay, reactants minus products. So it's going to be a difference of minus 674 kilojoules per mole. Okay, so you can actually illustrate this on an energy diagram where energy is on the y-axis and time is on the x-axis. Okay, so you've got your 264 kilojoules. Okay, there, your 3,320, so these are your products, and these are your reactants. Okay, and the difference is going to be minus 674 kilojoules. So more energy is given out, 3,320, than given in. So the reaction is considered exothermic, okay, because the difference is minus 674 kilojoules. Okay. If it was an endothermic reaction, then the reaction would have been positive instead, or the mixture difference would have been positive rather than negative. Okay. You've also seen in that diagram there was a giant hump in it. Okay. This is known as the activation energy. The activation energy is the minimum energy that must be put into a chemical reaction for it to occur. Okay, so you can think of it as pushing up a rock up a hill. Okay, so it requires energy obviously to get the rock to the top, but then once you get to the top, then gravity does its wonderful work and it is then continues rolling down the hill to point B. But there is still energy required to move it up to the top of the hill. Okay, and enthalpy is the amount of heat used or released in a reaction, and if the change of enthalpy delta H between the reactants and the products is negative, it is exothermic, and if it is positive, it is endothermic. Okay, and that's the example there. So reaction progress, you've got reactants of high energy. So in the previous example, that would have been your methane and oxygen, and the products were of lower energy, the carbon dioxide and water. Delta H would have been negative, so energy would have been released. If it was the opposite, then it would have been delta H would have been positive, and it would have been an endothermic reaction. Okay, quick learning check. So here is a reaction of a methanol being combusted to form carbon dioxide and water. Okay, there we go. So from your previous table, which I gave you the previous slide, can you work out what the delta H is for the reaction? Oh, and also a bit of water. Yeah, so can you work out what the energy changes, this enthalpy changes for this reaction? Okay, so you should have gone back to your previous slide with all the bond energies, and you should have plugged in the numbers. So the total for breaking the bonds is going to be 6 times 413 plus 2 times 360 plus 2 times 464 plus 3 times 497. That's the oxygen double bond. So the amount of energy required to break all those bonds is 5,617 kilojoules per mole. Whereas on the other side, for bond making, it's going to be 4 times 732, which is the carbon-oxygen bonds. You've got 4 of those. You've also got 8 times 464, all those OH bonds. So it's going to be 6,640 kilojoules per mole. So if you do the numbers, you subtract the products, the reactants from the products, you'll get minus 1,023. But you'll also have to remember to divide by 2 to get per mole, because you've got 2 methanol molecules. It's going to be minus 511.5 kilojoules per mole. So hopefully.
Collision theory and reactions 2. In this video you are going to learn what happens in a reaction, why some reactions are endothermic and some exothermic. When I was young I had a model set. Inside the box were the various components and an instruction book containing 80 models to build. On the first day I built a ship. The day after I wanted to build a tank, but I could not. Any idea why? I hadn't enough pieces left to build the tank. I had to take my ship to pieces and then use those pieces to build up the tank. You can liken this analogy to what happens in reactions. Consider the reaction between hydrogen and iodine to give hydrogen iodide. The reactants are what react and are on the left-hand side of the arrow in the equation, and the products are what are produced in the reaction are on the right-hand side of the arrow in the equation. We can represent what happens in this reaction by the diagram. A is the activation energy, which is the energy taken in to break the HH and the II bonds in the reactants. C is the energy given out when the new HI and HI bonds make to form the products. B is the net energy taken in, delta H, during the reaction. This is the energy difference between the energy taken in to break the bonds in the reactants and the energy given out when the new bonds make to form the products. The activation energy is the sufficient energy mentioned in the video Collision Theory and Reactions 1. Now consider the reaction between nitrogen and hydrogen to form ammonia. This is the Haber process. We can represent what happens in this reaction by the diagram. Again, A is the activation energy, which is the energy taken in to break the NN and the 3 HH bonds in the reactants. C is the energy given out when the 6 new NH bonds make to form the products. And B is the net energy given out during the reaction, delta H, which is the energy difference between the energy taken in to break the bonds in the reactants and the energy given out when the new bonds make to form the products. So, to recap, breaking bonds takes in energy, making bonds gives out energy. If more energy is taken in to break bonds than is given out when new bonds are made, the reaction is endothermic. If less energy is taken in to break bonds than is given out when new bonds are made, the reaction is exothermic.